What's up, everyone? Thanks for tuning into today's video. The focus of this video is going to be on single replacement reactions. In a single replacement reaction, one element is going to replace a second element that is in a compound. And what we're going to be doing is we're going to be creating a new element and a new compound in our products. We've discussed previously the general formula of all the different types of reactions in this unit. More specifically, with single replacement reactions, what we're going to see is that we're going to take a compound A and B with an element C. And as you can see from the reactants, when we produce our products, C then replaced B to give us a new compound, AC, and then B, which was in a compound before, is now by itself. In a real world example, where we have lithium reacting with iron 2 nitrate, I have these two elements underlined because these are the two elements that are going to replace each other in that single replacement reaction. When lithium and iron replace each other, what that's going to do is now iron is going to be the individual element where lithium is now a part of that compound where iron was previously. So all of this is made possible with one very important tool. And that important tool is called the activity series. And the activity series is a series of metals, and it's used to predict products in a single replacement reaction and identify the reactivity of metals with water and various acids. It can be used to predict the products in similar reactions that involve a different metal. And this is a tool that you guys are going to be able to use for anything involving single replacement reactions. It's not a tool that will be memorized. It's going to be given to you on a test, but it's obviously important that we know how to use this tool so that way we can use it effectively for an assessment. But as we look at the activity series that is included, we see that there is a separate activity series of metals where the more reactive metals are on the top of the list and our less reactive metals are down towards the bottom of the list. So typically we talk about reactivity and we relate that to stability. The less stable elements are going to be at the top, meaning they will react more easily, whereas the more stable elements are down towards the bottom, meaning they might not react as quickly as the ones that are on the top. Now, we also have an activity series for the halogens, the group 17 elements, and those are listed as such. And the nice thing about this is that all of these elements are actually in the same order as they appear on the periodic table, where fluorine is going to be the most reactive. And as we work down that group on the periodic table, those elements become less reactive. So with this activity series, there's obviously some skills that we're going to need to be able to achieve. And one of those skills is using it for the purpose of predicting whether or not a reaction will actually occur when we try to do a reaction. So what we're going to do to practice is 3 examples of being given single replacement reactions and being able to identify, first off, if that reaction is actually going to occur. If the reaction does occur, we're just going to include the letter R for reaction. And then if it does not react, or if a reaction will not occur, we're just going to write NR for no reaction. So in our first example, where we have potassium and copper are 2 elements that are potentially going to switch places, what we're going to want to do is obviously find where they're located on the activity series. I see that potassium is at the top of the activity series, meaning it is more reactive, or it will want to switch places with the less reactive element. So then I see that copper is well down towards the bottom. So because potassium is a more reactive metal, that means that it's going to be much more stable by forming a bond with this SO4 polyatomic ion called sulfate. So because potassium is currently by itself, and because it wants to be in a compound, what we would see is that the result of this reaction would be R, or reaction. This reaction would occur because potassium is more reactive and it wants to be a part of this compound. So we would see a reaction. For the second one, we have aluminum reacting with calcium chloride, CaCl2. And what we need to compare are the reactivities of aluminum and calcium in this case to determine if a reaction will or will not take place. So aluminum somewhere towards the middle of the activity series, right here. But we see calcium is slightly above it on the activity series. Now, calcium, being more reactive, wants to be a part of a compound or bonded to another element or elements. Because we see that calcium is already in the compound, the result of this reaction would be no reaction. The reason being is calcium is already stable by being a part of a compound. So these two elements, calcium and aluminum, would not replace each other, and we would produce no reaction in this case. All right, moving forward, last one here, getting a little bit more familiar with the activity series, which is then going to lead us into predicting the products. Let's compare magnesium and aluminum. I've got magnesium right here. Aluminum is directly below it. Even though they're right by each other, magnesium is higher up in the activity series, meaning that it is more reactive, wants to be a part of the compound. So because of that, we would see aluminum and magnesium switch places, producing two new products. So using the activity series is going to be very important for us in single replacement reactions, because now what we're seeing is that not all reactions will take place in a single replacement reaction. And now that we can identify whether or not a reaction does or does not take place, we can much more easily, or we can now be able to identify those reactions that do take place and then predict the products that will come out of that reaction. So let's see some examples of that. I want to take you guys through some written examples in your packet of where we'll see examples like this. And we're going to do that just, like I said, by writing things out. I'm going to stop sharing my screen here. And we have two examples that actually are present on page 11 in our packet. And let's just go ahead and see how these reactions kind of pan out and how we're going to go about predicting the products of if a reaction does take place. So I have my activity series here handy, because we will want to use this for our single replacement reactions. You guys will have one on the back of your periodic table. We also have one available in our packet, so just make sure you're keeping this nice and close while we're predicting these products. So in our first example, we have hydrochloric acid, HCl, reacting with magnesium. We obviously need to translate this into chemical equation form before we go ahead and predict any type of products or go forward with this. So hydrochloric acid, I gave you guys the formula for that. That's HCl. The word reacts with, we translate that to a plus sign. And that hydrochloric acid is going to react with magnesium, element Mg. Now we want to see what products might be produced out of this. Let's first compare our front two elements here. We've got hydrogen, and we're going to compare that to magnesium. So bringing our activity series in here. I know it's a little bit small, but I'm hoping that you guys have one nearby. I see that I have magnesium right here on the activity series, and hydrogen is considerably lower on the activity series. So what we see is that magnesium is actually going to want to switch places with this hydrogen. And now magnesium will form a bond with chlorine, and then hydrogen is going to be left by itself. So by producing a new compound with magnesium and chlorine, here we have another situation where we're going to need to be crisscrossing charges for the purpose of predicting some products. When we crisscross these charges, what that's going to give me is a formula MgCl2. So in the replacement of magnesium and hydrogen, when magnesium forms a bond with chlorine, what we will get is a product MgCl2. Now, because magnesium replaced hydrogen, hydrogen is now left by itself. And this brings up yet another topic that we've talked about, which are the diatomic elements, or the elements that occur in pairs. Those elements are hydrogen, nitrogen, oxygen, fluorine, bromine, and iodine. Hydrogen is one of these special 7 that needs a subscript 2, so we cannot forget that hydrogen H2 in the equation. So in this single replacement reaction, magnesium, switch places with hydrogen, producing magnesium chloride. We crisscross the charges, and hydrogen H2 because hydrogen is one of those big seven. Things to keep in mind, but we've been practicing this a lot, so I think you guys will be okay. Now, of course, you're probably thinking, hey, don't forget to balance this climb before we move on to the next one. You're right. We do need to balance this. We've got 2 chlorines here, 1 chlorine here, 2 hydrogens here, 1 hydrogen here. So this one's easy to balance. 2 in front of the HCl goes ahead and balances everything for us. So here we have a complete balanced single replacement reaction where we do produce a new product, a new compound, and a new product, a new element, hydrogen gas. All right, good example to start with, nice and easy. We're seeing that the crisscross charges and the big seven are present yet again. So let's see how that kind of comes into play for this next example. We have gold reacting with what is called phosphoric acid. Now, we haven't talked about how to write the formulas for acids. I'll be happy to provide you guys with that, and we'll make sure that those are provided in the case that they show up again. I didn't mean to leave that out of your guys' questions, so I'll be happy to provide that for you in the future. But at any rate, gold has the chemical symbol Au, reacts with plus H3PO4, phosphoric acid. So it looks like our elements to compare here are going to be gold and hydrogen from the activity series. Uh-oh, looks like we don't have gold on our activity series here. But using other resources, something like our lab, where we have a little bit more of an extensive activity series, I see that gold is way down here towards the bottom and hydrogen somewhere towards the middle. So finding another oopsie in this video, but that's okay. We'll make sure to address that. We're seeing good examples here. So because we know that gold is less reactive than hydrogen, gold being less reactive than hydrogen means that hydrogen wants to continue to be a part of a compound. So this is a nice one. Our result of this is just simply no reaction. Well, I'm actually about to see some of you right now. In this case, we have no reaction because gold will not switch places with hydrogen. We don't need to do anything else with this. We're good to go. We'll move on to the next one. Good luck on the practice problems, guys. Let me know if you have any questions. We'll make sure to talk about this in class. I love all of you. Have a great one. Bye.